Have you ever wondered why SpaceX rockets have so many engines? I mean, look at other rockets from huge agencies like NASA. Whether it's a smaller rocket or a really big one, they usually have like 4 or 5 massive engines. Because that's just how rockets have traditionally been built. So why did SpaceX suddenly decide to take a completely different approach? Is having a lot of smaller engines actually better than the way rockets have been built for decades? Or does putting 33 engines on a single rocket just create 33 more opportunities for something to go wrong? So first, let's take a quick trip through the history of putting a ridiculous number of engines on a rocket, because, unsurprisingly, SpaceX did not invent this idea. And once we understand why engineers started doing it, the whole 33-engine setup on Super Heavy makes a lot more sense. As I said, back in the day, rockets usually took the opposite approach. Instead of using a whole crowd of smaller engines, engineers would basically say, forget it, let's just build one absolutely enormous engine. And the Saturn V is probably the best example. Its first stage used just 5 Rocketdyne F1 engines, and each of those bad boys was enormous and produced roughly 1.5 million pounds of thrust. Put 5 of those monsters together, and Saturn V had around 7.5 million pounds of thrust at liftoff. SpaceX's Super Heavy, meanwhile, uses 33 Raptor engines and produces roughly more than twice Saturn V's liftoff thrust. Now, the 1950s and 1960s were a time when engineers loved pushing the limits and building bigger and more powerful machines. But as engines got bigger, so did the number of problems hiding inside them. One of the biggest headaches was something called combustion instability. Basically, inside a rocket engine, liquid oxygen and rocket fuel are being injected into the combustion chamber, mixed together, and burned at insane pressures and temperatures. If that combustion process starts producing pressure oscillations in the wrong way, those oscillations can feed back into the engine and become violently unstable. Basically, once that instability kicked in, the combustion became so violent that it could burn straight through the thrust chamber in just milliseconds. And when that happened, the hardware just started flying all over the place. In the case of the F1, combustion instability was a major problem during development. The engineers eventually traced much of the problem back to the injector plate, the part responsible for feeding propellants into the combustion chamber. Earlier engine designs had a different injector arrangement that naturally divided the initial combustion into smaller regions. But by the time the F1 was deep into development, completely redesigning the injector wasn't exactly a quick afternoon project. So instead, engineers added copper dividers called baffles between groups of injector elements. These created small compartments across the injector face, helping keep the combustion process stable. After a whole lot of testing, and presumably a whole lot of people staring nervously at test stands, the solution worked. So, what does this problem have to do with putting a lot of engines on a rocket? Well, the thing is, Soviet engineers ran into similar challenges when trying to build extremely powerful rocket engines. Instead of creating one gigantic combustion chamber and hoping it behaved itself, they took a different approach. Why not just divide the engine into several smaller combustion chambers? That's essentially what you see with engines like the RD-107. From the outside, it looks like one engine with multiple nozzles, but inside, it's actually using several separate combustion chambers, all fed by a common turbopump system. And the Soviets eventually took this idea to a pretty extreme level with their N-1 moon rocket. Its first stage had 30 engines. Now, there was one pretty major problem with the N-1. Its engine control system was nowhere near as sophisticated as what SpaceX has today. The N-1 used differential thrust for steering. Instead of physically tilting the engines to point the thrust in different directions, the rocket could steer itself by changing how much thrust individual engines produced. Basically, if you want the rocket to lean one way, you tell some engines to push a little harder and others to push a little less. Simple enough, until one of those engines decides to stop cooperating. If an engine failed, the control system suddenly had to deal with an imbalance in thrust. And depending on which engine failed and what was happening at the time, the system might have to compensate by changing the thrust of other engines or even shutting some of them down. And that's where things could get ugly, fast. One engine fails, the system compensates, that changes the loads on the other engines, another engine gets affected, and you get the point. The N-1 launched 4 times. All 4 launches failed. That's a pretty brutal track record. But it's important to understand that the Soviet moon program was operating under enormous political pressure to catch up with the United States. Every failure wasn't just a technical setback, it was a massive national embarrassment. And that pressure made it incredibly difficult to take the slow, boring, but very important path of engineering. Test something, find problems, redesign it, test it again, and repeat until everyone is sick of looking at the thing. There wasn't enough time, funding, or political support to properly redesign major parts of the rocket and spend years testing them before another launch attempt. So after the fourth N-1 failure, the Soviet lunar program effectively came to an end, which is honestly a pretty rough way for a moon rocket to retire. Anyway, just because one rocket tried putting a lot of engines on it and failed doesn't mean the concept itself was a bad idea. In fact, the advantages of using multiple engines are exactly why SpaceX brought the idea back. And it also fits surprisingly well with what Elon and SpaceX are trying to achieve, which is to reach 50,000 subscribers. Oh, sorry, that's actually my goal. But hey, you can help me get there. And in return, I'll keep bringing you more interesting spaceflight stories like this. So, what's the one big thing SpaceX rockets are famous for? Well, reusability, obviously. And that changes the engine problem quite a bit. Launching a rocket and landing a rocket are two very different jobs. During launch, you basically want one thing, a ridiculous amount of thrust. But during landing, you want something very different, precise, controllable thrust. And this is where having 33 smaller engines starts to make a lot more sense. A giant rocket like Super Heavy can't just use all of its engines the same way from liftoff all the way to landing. It doesn't need to. Instead, it can change how many engines are running depending on what the rocket needs at that moment. At liftoff, Super Heavy is carrying basically everything, the Starship, the fuel, and the giant chunk of rocket that comes with it. But by the time it comes back to Earth, most of that mass is gone. The booster is dramatically lighter. So if you tried to land using a giant engine that couldn't throttle very far down, you'd have a problem. But the thing is, rocket engines generally can't throttle all the way down to just a tiny fraction of their maximum thrust. So instead of asking one engine to produce, say, 5 or 10% of its maximum thrust, you can simply turn off some engines. And this is where having 33 engines becomes really useful. If Super Heavy needs a small amount of thrust for the final part of the landing, it can shut down most of its engines and operate with only a few. With 2 or 3 engines running, you're getting roughly the kind of low total thrust you need, while still retaining the ability to throttle those engines up and down. This gives Starship something that Falcon 9 doesn't have to the same degree. Falcon 9 usually has to perform what is often called a hover slam. And despite the name, there isn't actually a moment where the rocket politely hovers there and thinks about its life choices. Instead, the rocket times its final engine burn so precisely that it decelerates to essentially zero velocity right as it reaches the landing surface. It works incredibly well, but there isn't much room for improvisation. You can't just stop, hover for a few seconds, and figure things out. With Starship's larger engine count, SpaceX has more flexibility in how it manages thrust during the landing. So the 33-engine architecture isn't just about producing more thrust. It's also about giving the vehicle more control over that thrust. And there's another major advantage: redundancy. If you have only one engine, that engine had better be ridiculously reliable. But if you have multiple engines, you can design the vehicle to survive individual engine failures. The Saturn V actually used this philosophy too. Its first stage had 5 F-1 engines, and the rocket was designed with some engine-out capability. During the Apollo 13 launch, one of the F-1 engines shut down early. The remaining 4 engines kept the vehicle flying, although they had to burn longer to make up for the lost thrust. So having multiple engines can actually allow the reliability requirement for each individual engine to be somewhat less extreme. It's a bit like modern computer systems. Companies like Google and Amazon don't run everything on one gigantic computer and pray that nobody trips over the power cable. They use huge numbers of smaller machines. If one machine fails, the system can keep running because there are others available to pick up the work. That's very different from the old mainframe approach, where one giant machine did everything. And if that machine went down, well, maybe it's the sign to go outside to touch some grass. Another reason SpaceX likes this architecture is commonality. SpaceX wanted to use the same basic Raptor engine family on both Starship and Super Heavy. That makes a lot of sense when you look at what these vehicles actually need. Super Heavy has to generate an enormous amount of thrust because it's lifting the entire Starship and its payload off Earth. Starship itself doesn't need anywhere near that much thrust. Once it's in space, it doesn't have to fight Earth's full gravity anymore. And on the Moon or Mars, gravity is weaker still. So instead of designing one giant engine specifically for Starship and another giant engine specifically for Super Heavy, SpaceX can build around the same Raptor engine family and simply use different numbers and configurations of them. Starship has 6 engines, 3 optimized for sea-level operation and 3 designed primarily for vacuum, and those engines also provide redundancy. Super Heavy, meanwhile, needs an absurd amount of thrust just to get off the ground. But as I said, it doesn't necessarily need all 33 engines running for every part of the flight. As the booster gets lighter and higher up, it can keep going with fewer engines. And with 33 engines to begin with, the system also has spares in case a few decide to give up. So that's the reusability angle. But SpaceX has another pretty ambitious goal. They don't just want rockets to be reusable, they want to fly them as frequently as airplanes and use the same basic hardware across all kinds of missions. And that changes how you think about rocket design. Because if you're planning to launch a rocket once every few months, you can afford to treat it like a priceless piece of engineering. But if you're trying to launch all the time, suddenly you care about something much less glamorous. How quickly can we build the damn thing? And that connects directly to the decision to use lots of smaller engines. Let's start with manufacturing. If you want to build a giant rocket engine, you need giant manufacturing equipment to build it. Everything gets bigger. The machines, the tooling, the facilities, the transportation, and, inevitably, the amount of money required to do all of it. But smaller engines are much easier to manufacture in large numbers. You can build an assembly line around them, automate more of the process, and produce engines in batches. And once you're producing hundreds or thousands of engines, you start getting something every manufacturer loves: economies of scale. The more engines you make, the more opportunities you have to improve the manufacturing process and drive down the cost of each individual engine. And that is extremely important for SpaceX. Because SpaceX isn't trying to build a handful of beautiful, handcrafted rocket engines. They're trying to build a lot of engines, like really a lot. If Super Heavy uses 33 engines per flight and you're flying frequently, the number of Raptors you need starts adding up very quickly. So instead of asking, how do we make one enormous engine as cheaply as possible, SpaceX can ask, how do we make thousands of these engines as cheaply and quickly as possible? And the same logic applies to testing. Whether an engine is huge or relatively small, you still have to test it. You still need a test stand, you still need propellant, you still need sensors, you still need a giant area where the engine can scream at full power without turning the neighborhood into a new geological feature. But a larger engine makes almost everything around the test more difficult. It requires more propellant, larger equipment, more infrastructure, and more complicated logistics just to move the thing around. And history gives us some pretty good examples of how annoying this can get. During the Space Shuttle era, NASA needed specialized equipment to transport some of the giant rocket hardware. Because, unsurprisingly, you can't exactly throw a massive rocket component onto a normal train and tell the conductor, yeah, just be careful with that. With smaller engines, the entire process becomes easier to scale. You can have multiple test stands operating at the same time. One engine is being tested while another is being assembled, another is being inspected, and another is already heading toward a rocket. That matters enormously if your goal is high launch frequency. And then there's another underrated advantage: off-the-shelf technology. When you're designing a rocket engine from scratch, you don't want to reinvent every single component if you don't have to. If an existing pump, valve, sensor, computer, or manufacturing process can do the job, using it or adapting it can save a huge amount of time and money. Imagine you need an engine producing around 55,000 pounds of thrust. If there's already a well-understood, inexpensive engine design producing around 50,000 pounds, you might be tempted to make it bigger. But that could mean redesigning the turbopump, combustion chamber, injector, cooling system, test equipment, and a whole bunch of other things. At some point, Adding 5,000 pounds of thrust can create way more engineering work than it's worth. Sometimes it's cheaper and easier just to use another engine. And that gets to the heart of SpaceX's approach. They're not optimizing the rocket around the idea that fewer engines must automatically be better. They're optimizing the entire system around high production, low cost, rapid turnaround, and frequent launches. Because if SpaceX really wants to operate Starship more like an airline than a traditional government rocket program, then the rocket can't just be reusable. It has to be mass-produced, easy to test, relatively cheap to maintain, and available in large numbers. Basically, SpaceX doesn't just want to build a rocket. They want to build a rocket factory. And once that's the goal, having 33 engines on one booster starts looking a lot less like overkill and a lot more like a manufacturing strategy.